4. Can we predict the future? In ancient times, the world must have seemed pretty arbitrary. Disasters such as floods, plagues, earthquakes, or volcanoes must have seemed to happen without warning or apparent reason. Primitive people attributed such natural phenomena to a pantheon of gods and goddesses who behaved in a capricious and whimsical way. There was no way to predict what they would do, and the only hope was to win favor by gifts or actions. Many people still partially subscribe to this belief and try to make a pact with fortune. They offer to behave better or be kinder if only they can get an A grade for a course or pass their driving test. Gradually, however, people must have noticed certain regularities in the behavior of nature. These regularities were most obvious in the motion of the heavenly bodies across the sky. So astronomy was the first science to be developed. It was put on a firm mathematical basis by Newton more than 300 years ago, and we still use his theory of gravity to predict the motion of almost all celestial bodies. Following the example of astronomy, it was found that other natural phenomena also obeyed definite scientific laws. This led to the idea of scientific determinism, which seems first to have been publicly expressed by the French scientist Pierre-Simon Laplace. I would like to quote to you Laplace's actual words, but Laplace was rather like Proust in that he wrote sentences of inordinate length and complexity. So I have decided to paraphrase the quotation. In effect, what he said was that if at one time we knew the positions and speeds of all the particles in the universe, then we would be able to calculate their behavior at any other time in the past or future. There is a probably apocryphal story that when Laplace was asked by Napoleon how God fitted into this system, he replied, "Sire, I have not needed that hypothesis. I don't think that Laplace was claiming that God didn't exist. It is just that God doesn't intervene to break the laws of science." That must be the position of every scientist. A scientific law is not a scientific law if it only holds when some supernatural being decides to let things run and not intervene. The idea that the state of the universe at one time determines the state at all other times has been a central tenet of science ever since Laplace's time. It implies that we can predict the future, in principle at least. In practice, however, our ability to predict the future is severely limited by the complexity of the equations and the fact that they often have a property called chaos. As those who have seen Jurassic Park will know, this means a tiny disturbance in one place can cause a major change in another. A butterfly flapping its wings in Australia can cause rain in Central Park, New York. The trouble is, it is not repeatable. The next time the butterfly flaps its wings, a host of other things will be different, which will also influence the weather. This chaos factor is why weather forecasts can be so unreliable. Despite these practical difficulties, scientific determinism remained the official dogma throughout the 19th century. However, in the 20th century, there were two developments that show that Laplace's vision of a complete prediction of the future cannot be realized. The first of these developments was what is called quantum mechanics. This was put forward in 1900 by the German physicist Max Planck as an ad hoc hypothesis to solve an outstanding paradox. According to the classical 19th century ideas dating back to Laplace, a hot body, like a piece of red-hot metal, should give off radiation. It would lose energy in radio waves, the infrared, visible light, ultraviolet, X-rays, and gamma rays, all at the same rate. This would mean not only that we would all die of skin cancer, but also that everything in the universe would be at the same temperature, which clearly it is. However, Planck showed one could avoid this disaster if one gave up the idea that the amount of radiation could have just any value, and said instead that radiation came only in packets or quanta of a certain size. It is a bit like saying that you can't buy sugar loose in the supermarket, it has to be in kilogram bags. The energy in the packets or quanta is higher for ultraviolet and X-rays than for infrared or visible light. It means that unless a body is very hot, like the sun, it will not have enough energy to give off even a single quantum of ultraviolet or X-rays. That is why we don't get sunburn from a cup of coffee. Planck regarded the idea of quanta as just a mathematical trick and not as having any physical reality, whatever that might mean. However, physicists began to find other behavior that could be explained only in terms of quantities having discrete or quantized values rather than continuously variable ones. For example, it was found that elementary particles behaved rather like little tops, spinning about an axis. But the amount of spin couldn't have just any value. It had to be some multiple of a basic unit. Because this unit is very small, one does not notice that a normal top really slows down in a rapid sequence of discrete steps, rather than as a continuous process. But for tops as small as atoms, the discrete nature of spin is very important. It was some time before people realized the implications of this quantum behavior for determinism. It was not until 1927 that Werner Heisenberg, another German physicist, pointed out that you couldn't measure simultaneously both the position and speed of a particle exactly. To see where a particle is, one has to shine light on it. But by Planck's work, one can't use an arbitrarily small amount of light. One has to use at least one quantum. This will disturb the particle and change its speed in a way that can't be predicted. To measure the position of the particle accurately, you will have to use light of short wavelength, like ultraviolet, X-rays, or gamma rays. But again, by Planck's work, quanta of these forms of light have higher energies than those of visible light. So they will disturb the speed of the particle more. It is a no-win situation. The more accurately you try to measure the position of the particle, the less accurately you can know the speed, and vice versa. This is summed up in the uncertainty principle that Heisenberg formulated. The uncertainty in the position of a particle times the uncertainty in its speed is always greater than a quantity called Planck's constant, divided by twice the mass of the particle. Laplace's vision of scientific determinism involved knowing the positions and speeds of the particles in the universe at one instant of time. So it was seriously undermined by Heisenberg's uncertainty principle. How could one predict the future when one could not measure accurately both the positions and the speeds of particles at the present time? No matter how powerful a computer you have, if you put lousy data in, you will get lousy predictions out. Einstein was very unhappy about this apparent randomness in nature. His views were summed up in his famous phrase, "God does not play dice." He seemed to have felt that the uncertainty was only provisional and that there was an underlying reality in which particles would have well-defined positions and speeds and would evolve according to deterministic laws in the spirit of Laplace. This reality might be known to God, but the quantum nature of light would prevent us seeing it, except through a glass darkly. Einstein's view was what would now be called a hidden variable theory. Hidden variable theories might seem to be the most obvious way to incorporate the uncertainty principle into physics. They form the basis of the mental picture of the universe held by many scientists and almost all philosophers of science. But these hidden variable theories are wrong. The British physicist John Bell devised an experimental test that could falsify hidden variable theories. When the experiment was carried out carefully, the results were inconsistent with hidden variables. Thus it seems that even God is bound by the uncertainty principle and cannot know both the position and the speed of a particle. All the evidence points to God being an inveterate gambler who throws the dice on every possible occasion. Other scientists were much more ready than Einstein to modify the classical 19th century view of determinism. A new theory, quantum mechanics, was put forward by Heisenberg, Erwin Schrödinger from Austria, and the British physicist Paul Dirac. Dirac was my predecessor, but won as the Lucasian professor in Cambridge. Although quantum mechanics has been around for nearly 70 years, it is still not generally understood or appreciated, even by those who use it to do calculations. Yet it should concern us all, because it is completely different from the classical picture of the physical universe and of reality itself. In quantum mechanics, particles don't have well-defined positions and speeds. Instead, they are represented by what is called a wave function. This is a number at each point of space. The size of the wave function gives the probability that the particle will be found in that position. The rate at which the wave function varies from point to point gives the speed of the particle. One can have a wave function that is very strongly peaked in a small region. This will mean that the uncertainty in the position is small. But the wave function will vary very rapidly near the peak, up on one side and down on the other. Thus, the uncertainty in the speed will be large. Similarly, one can have wave functions where the uncertainty in the speed is small, but the uncertainty in the position is large. The wave function contains all that one can know of the particle, both its position and its speed. If you know the wave function at one time, then its values at other times are determined by what is called the Schrödinger equation. Thus, one still has a kind of determinism, but it is not the sort that Laplace envisaged. Instead of being able to predict the positions and speeds of particles, all we can predict is the wave function. This means that we can predict just half what we could according to the classical 19th century view. Although quantum mechanics leads to uncertainty when we try to predict both the position and the speed, it still allows us to predict, with certainty, one combination of position and speed. However, even this degree of certainty seems to be threatened by more recent developments. The problem arises because gravity can warp spacetime so much that there can be regions of space that we can't observe. Such regions are the interiors of black holes. That means that we cannot, even in principle, observe the particles inside a black hole. So we cannot measure their positions or velocities at all. There is then an issue of whether this introduces further unpredictability beyond that found in quantum mechanics. To sum up, the classical view put forward by Laplace was that the future motion of particles was completely determined if one knew their positions and speeds at one time. This view had to be modified when Heisenberg put forward his uncertainty principle, which said that one could not know both the position and the speed accurately. However, it was still possible to predict one combination of position and speed. But perhaps even this limited predictability might disappear if black holes are taken into account. Do the laws governing the universe allow us to predict exactly what is going to happen to us in the future? The short answer is no and yes. In principle, the laws allow us to predict the future. But in practice, the calculations are often too difficult.